Okay, hi. So my name is Jordan. I work on the Microsoft Offensive Security Research team. And today I'm going to be talking to you about hacking Hyper-V. And well, so for those of you who haven't heard of us, Microsoft OSR's goal is basically to just write exploits for Microsoft products, right? We have done non-Microsoft products at a time, but that is not our primary focus. Basically, we want to just try and find every interesting security target in terms of products that we are shipping, so things like Windows, Xbox, phones, once upon a time, web browsers, and all that kind of stuff, and try to hack them in such a way that we will be able to not only find new vulnerabilities, but also actually exploit them such that we can kind of identify exploit techniques and invariants and try to mitigate those. And so that's actually how this talk ended up being in this track, is that this is very much going to be an exploit talk, right? I'm going to go through what Hyper-V is, how it works, how we found vulnerabilities in it, and then how we're going to actually exploit them. But on top of that, I am also going to talk to you about, well, what are we actually doing about these vulnerabilities, right? We don't just want to fix them. We want to try and put mitigations into the product that make it such that even if the vulnerabilities still existed today, which to be clear, they do not, we have fixed them, they would not be exploitable, or at least much harder to exploit. On top of that, if I manage to fix it in time, there will be a live demo. So stay for that, even if you don't care about the rest of the content, because it should be pretty cool. So what is Hyper-V, or Hyper-V, like some people like to pronounce it? Hyper-V is basically this, right? If you want to use Hyper-V on your computer, this is what you're going to see. It's your Windows 10 machine. You have your desktop right here. That's the whole thing. And on top of that, you have one window, which has its own tiny desktop in the middle. And it turns out what's going on here is you actually have two operating systems that are running. And so just to kind of introduce some of the nomenclature here, you have the host OS, which is what, it's like Windows 10, which is running like basically bare metal, not quite. Which is what is hosting like your machine. It's what's actually running on your computer. Then you have the guest OS, the guest operating system, which is running within a virtual machine that is being hosted by this host OS. Throughout this talk, I'm only going to talk with an example of just having one guest OS, so just one virtual machine running at a time, just for simplicity. In practice, obviously, you can have way more than that. That's the whole point of virtual machines. And, well, you might be wondering at this point, okay, this is kind of cool. I don't quite get why you might want to do that. Why do you want to run virtual machines on a computer? Well, basically, the whole point is isolation, right? This way, we are actually able to have multiple people running multiple operating systems on a single server, basically, and each one of them can do its own thing and do its own thing without affecting the security of all the other virtual machines running on the server. And so this basically powers the cloud, right? And the idea is that if you kind of are able to break out of a guest OS, break out a virtual machine, well, you kind of compromise the security of not only the server, but also every other virtual machine on the server, and, well, that's bad for the cloud, which is why this is actually a really important security boundary and something that we are always working tirelessly to kind of protect. So now taking a lower level look at what Hyper-V is. Once again, to the right, you're going to have the guest OS. To the left, you're going to have the host OS. At the top, you have the hardware. This is basically your server. It's going to be your CPU, your RAM, your permanent storage, your network card, all that crap. What you're going to notice is that in between the between the OS layer, you're actually going to have something called the hypervisor. It's that yellow box there. The hypervisor, you can basically think of that as being the operating system's operating system, right? It is what decides which virtual machine is able to use which CPU core at a given time, which virtual machine is able to use which section of memory, and all that. So it really is like its own kind of tiny operating system that is giving access to various resources to the rest of the to the actual virtual machines that are running below. And then if you kind of take a look at the level below, well, you're going to see the host OS and the guest OS again. What you're going to see as different between the two is that the host OS has this little nub at the top left there, which basically gives it access to the hardware directly. And you're not going to see the same nub for the guest OS. And the reason is the guest OS actually does not have direct hardware access. You are also going to see a little blob in the middle called VMBus, which basically allows the host OS and the guest OS to communicate directly. Going to go into more detail as to how that works. But that's essentially how that works. The interesting part about this is you might be thinking, well, okay, we have the guest OS, does not have access to hardware. Well, how does it do its thing, right? Let's say we have a process, foo.exe is running within the guest OS user mode. Well, this process wants to be able to access data on the hard drive, right? Well, typically what would happen is foo.exe starts talking to its own kernel, its own I/O stack, which is living within that kernel, and that I/O stack will just start talking to the hardware directly. But once again, the guest VM does not have access to that, so how does it do that? Well, instead, it's going to talk to a driver that is living within the guest operating system. In this case, it's going to be called store VSC, store for storage, VSC for virtualization service client, I believe. And essentially, that provides a compatibility layer with the rest of Hyper-V. And so store VSC is going to function by talking to something called store VSP, which is going to be hosted on the host OS side. And it's going to do that through VMBus, not going through the hypervisor, just straight up through VMBus. And store VSP then is going to talk to its own I/O stack and going to talk to the storage hardware. And what that gives us is, if you want to think about this whole virtual machine system as kind of a sandbox model, then you can think of the host OS as being the broker process. And then you can think of the guest OS as being the sandbox process, right? The idea is that every access to every resource that the guest OS tries to do has to go through the host OS. And therefore, the host OS can enforce arbitrary restrictions on that. So for example, specifically here, you're going to have the host OS allowing access to files that are within the guest OS's virtual hard disk, but it's not going to allow access to files that are on the host OS's C drive, right? You don't want to be able from the guest OS to modify, C/system32/whatever, because then you can just take over the host OS and things are bad. So that's essentially how that works. Now, I'm saying, okay, this is going through VMBus, which so far has been kind of a black box between the two, or I guess like a yellow box in this case. So how does that work? Well, as I mentioned, it actually just goes straight through VMBus from the guest OS to the host OS, and vice versa. And well, you might be thinking both the host OS and the guest OS have access to the hypervisor that can both talk to it, so why not just send those messages through there? Well, the reason is basically, context switches are expensive. If you just try to context switch into the hypervisor and out every time you try to send a message, we're not going to be able to do that at a very high frequency or anything like that. So instead, we introduced this concept of shared memory between the guest and the host. And so if you take a look here, you're going to have at the top physical memory, and then you're going to have a block of physical memory that is actually shared between the guest and the host. Like it's mapped in both virtual machines, or like in both partitions of Hyper-V, right? And the idea then is VMBus can leverage this shared memory concept and just kind of interpret one piece of shared memory as a ring buffer, and then whenever you want to send a packet from the guest to the host, well, essentially, you're just going to have your VSC, your virtualization service client, send a packet over a VMBus. VMBus is going to then copy it into this ring buffer. Because this ring buffer is shared between the guest and the host, once it's copied, it just shows up everywhere. It's in physical memory. It is in both the guest and the host. Everything is all good. And then at that point, you just kind of alert the host, like, hey, there's a packet. Maybe check it out. And that's what the host OS does, and everything's all good. Now, the thing is, because this is a ring buffer, by its very nature of like that data structure, it's going to be very serialized, and so it's not necessarily appropriate for every single type of memory that you're going to have to, every type of packet that you're going to have to send between the guest and the host, right? Let's think about something like storage, like just mentioned. That's going to be a lot of data at a very high frequency, typically, or even networking, right? And so having to send all that data through a ring buffer every time, that means having to copy data in and out every time. And that means serializing all those operations. That's not necessarily tractable. It's not scalable. So instead, we introduce a concept of basically you can attach a piece of shared physical memory to a packet. In this case, in the case of Hyper-V, we call that a GPADL. GPADL stands for Guest Physical Address Descriptor List. If you're familiar with Windows kernel concepts, that is basically an MDL, right, a memory descriptor list, but except that it spans the boundary between, different memory partitions. And so basically, a packet has the ability, when it wants to send a big piece of data, for example, from the guest to the host, to instead of copying that into the ring buffer, it's just going to say, tell VMBus, okay, well, I want to send this piece of data. It's in this piece of physical memory. Tell the host that it is allowed to map it out, and then either read or write data to and from it, and then everything's all good. And so at this point, you basically know everything about Hyper-V that I do. Everyone in this room is like a Hyper-V expert. And so now we can start diving deeper into all the concepts that are going to apply more specifically to the component that we're actually going to exploit today. And this component is called VM switch. So looking at this this kind of diagram from earlier. That diagram, it shows the exact same thing, except that now, instead of showing access to storage hardware, we are showing access to networking hardware, right? And so VM switch is basically just that. It is a virtual switch that gives access to the various network hardware that is accessible from the host OS to the guest OS. And so any network packets basically that is coming from the guest OS or going to the guest OS has to go through VM switch. And so it is it's a fairly complex component, and obviously it is something that is going to require a fair amount of complexity for one thing, but also because it is going to be handling all this data that is a very high frequency and a lot of high volume as well, is going to require some interesting engineering. So taking a look at how this works, basically this is the initial. I'm going to try to show you like the initialization sequence of VM switch. Oh, also, yeah, I did miss a little part. So the way that VM switch is actually implemented is it emulates a network card, right? It uses the RNDIS protocol, which stands for Remote NDIS Protocol, which is actually something that a lot of people are familiar with. I'm not a networking expert. As far as I understand, the Remote NDIS Protocol is just something that has been used for a while by Microsoft to implement basically USB network cards, right? So you can kind of think of VM switch as implementing a USB network card over VM bus. So really, we're just changing the mode of transportation, but then implementing like a completely standard protocol. And so nothing's changed there. And so that's kind of the thing that's interesting, is that then VM switch has to handle two types of messages, right? It's going to first handle messages that are specific to VM switch. And so that's going to be an example. There's basically typically the first message that you're going to be sending over VM bus from the guest to the host is just going to say, okay, hi, I want to talk to VM switch protocol version 5, please. Then VM switch is going to be like, okay, cool. And after that is going to say, okay, now that we talk the same language, the same VM switch language for VM switch messages, I want to be able to talk to you in remote NDIS version 6.3, right? And at that point, again, hopefully VM switch is like, okay, cool, whatever. But after that is going to start doing more setup that is, again, very specific to VM switch that is going to then allow it to send RNDIS messages. And the things that are going to happen here is basically the guest OS is going to allocate two buffers, one called the receive buffer and one called the send buffer. And basically the send buffer and the receive buffer are both going to be shared memory buffers. So again, like mentioned earlier, they're basically defined as GPADLs allocated by the guest. The guest sends them over to the host, and then the host and the guest are able to use that as additional communications channels in addition to the VM bus ring buffer, right? And so then the send buffer is going to be used by the guest OS to send RNDIS messages to the host, and I'm pretty sure you can guess what the receive buffer is going to be used for, so that's basically it. Now, going deeper into how this send buffer and the receive buffer, how those buffers work. Well, as mentioned, one of the reasons that you might want to have these buffers, these shared buffers in addition to ring buffer, is that you want to be able to send data at a higher frequency in parallel, and maybe even like more volume, whatever. The thing is, if you want to be doing things in parallel, well, you can't just have one buffer that allows you to just send one message at a time. So as soon as the guest OS allocates those buffers and sends them over to the host, what happens is the host actually subdivides them into smaller sub-allocations, which might seem like a trivial detail, but it will come up later, so bear with me. And at that point, once that's done, the guest OS is actually able to start sending and receiving RNDIS messages. And so let's say it wants to send an RNDIS query message. It first generates it, copies it into the send buffer, sends a VM bus message to the host OS to say, hey, check it out. There's a message in the send buffer, sub-allocation 0. You should really process that. VM switch is like, okay, cool, grabs it, acknowledges that it grabbed it, so now the send buffer is free again, can be used if necessary. Then it processes it, generates a response, puts it into the receive buffer, and then tells the guest OS that there's something in the receive buffer, sub-allocation number 2. Guest OS grabs it, is very happy, and just acknowledges that it has grabbed it, and once again, both the send buffer and the receive buffer are completely free. And so that's how you are able to just kind of use these buffers in a way that is more parallel than than just sending stuff through through VMBus. And the reason for that is that you are actually, this is basically going to explain it, taking a closer look at how these things are processed on the hostOS side. The thing is, you have actually a number of threads, right? And only one thread is ever going to handle VMBus messages, right? That's basically a VMBus thread. It belongs to VMBus. Whenever it sees a message coming from VMBus, it is going to handle it, call a callback from VMSwitch, and then only then handle the next message. So these operations are completely serialized. And the way that these send buffers actually allow parallelism is by introducing new threads. And so to have another example that kind of illustrates this a little better, let's say we have RNDisk query, RNDisk set messages in both slots of this send buffer. The guest OS tells the host OS, okay, here we have these messages. So the host OS VMBus channel thread receives them. Instead of just actually processing it directly, it's just going to put it into a queue. And at that point, it's just going to acknowledge it, grab the second message in the same way, just going to put it into a queue. And then after that, only once those messages have been handled, well, you actually have an additional two threads, which are going to be the RNDisk worker threads. In practice, there's more than just two, but for simplicity, I'm going to say there's two. And those threads can run in parallel. They can both each complete a message or do whatever, just like process them. And then they can both each copy the results of those messages to the receive buffer, acknowledge that they have been processed and that the receive buffer contains the responses, and then the guest OS can read back those responses and do its thing. So I realize that this is all a little dense, but I swear that all this information is actually useful for understanding vulnerability and then the underlying exploit. So let's get into that. How do we exploit a system like this? Well, one thing that I always like to do is kind of look at initialization sequences, just because they typically have, well, they sometimes have weird state machines, and you're not always sure if the developer has really thought through what might happen if you send a message out of order, or like one message more than once, or something like that. And that's exactly what kind of bug this actually was. So taking a look back at this diagram from earlier, right, where you just have the very first two messages that are being sent over by the guest OS to the host OS. They just set the protocol versions, everything's cool. But after that, what happens is, well, the guest OS wants to send over a receive buffer, so it first allocates a gpaddle, right, a shared piece of memory, and it sends it over to the host, saying, okay, use gpaddle 0 as your receive buffer. Well, it turns out at the time, one of the things that the developers had not thought of was that an attacker might actually want, well, like just a guest OS might send this receive buffer message more than once. And taking a look at what happens, well, if I allocate a second gpaddle and then send it over, is going to just update the receive buffer pointer to point to that second gpaddle. And if I do that a third time, that happens again, which doesn't seem like a big deal, right? The only thing that's kind of weird is, well, those gpaddles 0 and 1 are still mapped in the host OS, right? And at that point, you might think, okay, well, this is kind of a bug. It doesn't seem like a big deal. It seems like it might be, a memory leak, possibly, which could lead to a DOS. In practice, it doesn't, but it could be a problem. But it's not a big deal until you start looking more closely at how this update of a receive buffer, which was not ever meant to be an update as much as an initialization process, actually works. And it actually works in 3 steps, which only exists because, if you'll recall, the host OS is responsible for sub-allocating these receive buffers into smaller, tiny buffers, right? And so that means that it actually keeps track of 2 things. It keeps track of a buffer, of a pointer to the buffer itself, and then it keeps track of the boundaries of these sub-allocations. And so it does the initialization of the receive buffer in 3 steps. First, it updates the pointer to the buffer. Then it updates. Then it generates the boundaries for these new sub-allocations, and then it updates the boundaries for these sub-allocations. And what you can see is that those 3 operations are not in any way atomic, right? There is going to be time that happens between the beginning of this function and the end of this function. And in addition to that, if you take a look at the code, there is no locking, or at least no relevant locking for us. And so trying to visualize that a little bit more, let's say I'm the guest, and I say, okay, please use gpaddle 0 as your receive buffer. Host OS is like, okay, totally cool. I'm going to generate my bounds. I'm going to update my bounds. Everything's all cool. It acknowledges that. And then let's say I'm a guest OS, and I wanted to use gpaddle1, which is slightly smaller, but that shouldn't be a problem. It's like, OK, cool. I'm going to update my, my receive buffer pointer. And, well, because it has only updated the receive buffer pointer in that very first step, it has not yet generated the new bounds. And so those old bounds, which are bigger than this new receive buffer, are still being applied to the new receive buffer, right? And so then the second step, well, is generating the new bounds. Well, they're still not being applied. And only after this third step, when the bounds of the stub allocations are actually updated, do you see the result. And that's basically the RC vulnerability, right? Is that during these two, like this tiny window in between those two steps, you can actually, if you are able to get a parallel worker thread, because those are the threads that are writing to that receive buffer, if you can get one of those threads to write in parallel to the receive buffer while you're updating the receive buffer, which is a tiny window of maybe like a few hundred cycles, then you're actually going to be able to write data out of bounds in the host OS. And that's kind of a great bug for us. Now, in practice, exploiting this is not necessarily trivial, right? You need basically three things. You need to be able to control the data that's going to be written out of bounds, because if you don't control it, it's just garbage. Well, it might be exploitable. It's very unlikely, though. Then you need to actually be able to win the race, right? You need to be able to somehow massage the execution state on the host OS such that that one thread is going to write that one piece of data to that one buffer at the exact right time, which is not really trivial. It basically means getting the host OS to race itself. It's kind of weird. And the third thing is you need to actually be able to place a corruption target at a known offset of your receive buffer in such a way that writing out of bounds from receive buffer is actually going to overwrite a critical data structure. So those are three things that we need to actually exploit the vulnerability. None of this is trivial, but hopefully it is all doable. And that's going to be what I'm going to try and cover here. So first thing, can we actually control what's being written out of bounds? The short answer is yes. Basically, if you take a look at the RNDIS protocol, you're going to have a few sets of messages, and well, you're going to have a few message types. Sorry. The first message type that is interesting is well, the message type is specifically interesting here is the RNDIS query message. The way that the RNDIS query message works is you give the host OS an OID, like an ID for some kind of piece of data that you want. It could be something like your MAC address or something like that, right? And then it's going to return it in this information buffer that is embedded inside a packet that is going to be sent back to the guest OS. So the idea here is actually pretty trivial. You just find an OID that you can set arbitrary data into through the RNDIS set message, and then you just use the RNDIS query message to have the host OS send you back that data in such a way that it's going to overwrite other data out of bounds and do blah blah blah. So this one, it turns out, is actually not a big deal, not a big problem. So that's cool. One down, two to go. Oh, maybe three. We'll see later. Now the next thing is you need to actually be able to win that race between the host and the host, right? You need to be able to get one of those two worker threads to somehow write to the receive buffer at the exact right time. And so if you think about it, there's really two ways to go about it. Either you're going to have one single message that is going to be written to the receive buffer at the exact right time, which totally works. You really only need one message to be written there, right? The thing is, that's not trivial for the reason that, well, you don't necessarily control when that one message is going to be written out to the receive buffer, right? You don't, as an attacker, you don't get to tell the host OS, okay, like please wait for like n number of milliseconds or nanoseconds or however many units of time you want until you write it to my receive buffer. In addition to that, well, even if you could do that, it's not trivial to know exactly how long you're supposed to wait in order to hit that window. So maybe an easier way to do it would just be to have the host OS just write to that receive buffer all the time, right? Maybe message after message after message, which in a way doesn't look impossible, right? Because we do have that message queue, and we do have these two worker threads in parallel. So if it just handle message after message after message, well, it should just be continuously written to the receive buffer, right? Wrong. It doesn't work that way. Each receive buffer each worker thread is actually just going to handle its message, right? It just generates a complete message, writes each complete message over to the receive buffer, and then you would expect it to maybe handle the third receive buffer, the third RNDIS message, sorry. But no, it doesn't. It kind of just locks until it has received confirmation that the guest OS has actually read the message out of the receive buffer. In a way, it makes sense, right? Because the receive buffer only has so many slots in it, and well, the host OS doesn't want to overwrite one slot before the guest OS has read out of it, so it needs to wait for a signal to say, okay, the coast is clear, you can actually write to the receive buffer again. Unfortunately, the reason that this is impractical for us is that you can totally, of course, tell the host OS, like, okay, the coast is clear, everything's good, but you have to do it through VMBus. Like, once you've done it through, like, once you send this acknowledgement message through VMBus, it's going to unlock the thread, and it's then going to handle this third RNDIS message, and everything's going to be good. But because this message has to come from VMBus, which is the serialized operation which also handles the update of receive buffer, it is impossible for it to happen at the same time as the update of receive buffer. And so basically, this just can't work, which kind of sucks. So we're back to the other option. And the other option is simply to try and win the race with a single RNDIS message being written out to the receive buffer. And well, how do we do that? As mentioned, we basically want to be able to control the delay between the time that we send that message and the time that's actually written to the receive buffer. And well, there's no by design way to do that, but maybe if we're able to find a way to send a message, like place a message in that queue that's going to be handled somehow by VM switch without locking one of those worker threads, then we could just, like, you know, queue up a bunch of those messages, and then the number of messages that we have queued up before our actual target message will become, you know, proportional to the amount of, like, the delay that will happen before the actual out of bounds write happens. And so it turns out there is actually such a message. It's if you send a RNDIS message that is malformed, for example, you know, too small for its type or something like that, then the VM switch RNDIS worker thread is just going to discard it. And if it discards it, well, it's not going to write anything out to the receive buffer. It's not going to lock itself, and it's just going to handle the next one. And so that's where the cascade of failure idea comes into play. Basically, you just kind of queue up a bunch of messages that you know are going to fail, right? And they're all going to be handled one after the other as soon as this thread is unlocked, and then it's going to handle your actual message that should do the out of bounds write. And so that's what's happening here, right? Let's say we have these two worker threads being locked right now, right? They're both locked. We unlock one of them over VMBus in a completely serialized way. And then after that, it starts handling message after message after message after message. None of them write to the receive buffer, except for the very last one. And so that's basically, well, that's exactly what I was describing earlier, is that now we have the ability to control the delay between the time that the VM switch starts handling messages and the time that the out of bounds write might happen. Now, the thing is, we need to get the number of failed messages exactly right in order to actually hit the race, actually hit the target for us. And, well, that's not trivial because you can't just guess that number, right? I mean, you might be able to if you're really lucky, but it's unlikely. You want to do it in the fewest number of attempts, ideally. And so, well, you might actually be able to search for that number of messages, right? Because if you're able to tell if the message was written out of bounds too early or too late, you know, if it was too early, you just increase the number of failed messages. If it was too late, you decrease the number of failed messages. And you can just do something like use an algorithm called binary search. And just use that to kind of do your thing. And it turns out you can actually tell if a message was too early or too late, right? If it's too early, the message is going to be written within bounds of the first receive buffer that you used, right? And so as an attacker, because that receive buffer is still mapped in your memory space, you can just read out of it and say, okay, well, something was written there, so I'm pretty sure it was too early, so okay, I'm just going to increase n. Okay, well, now you've increased n too much and you're too late, so, well, turns out, same thing. The receive buffer at that point is completely valid, and so the boundaries are going to make it such that the new message was written in the new receive buffer at the very end. So again, you can just kind of read that and see. And now the final thing is, if you were just right at the exact right time, then the message is, by definition, just going to be written out of bounds, and at that point you can't see it. And so, well, that's your signal, right? That tells you that your thing was written out of bounds, and everything is good. So at this point, we are able to control what's written out of bounds, and we're actually able to write data out of bounds, which is awesome. The only thing that's missing is, well, what do we actually write out of bounds? What do we corrupt? And that was not trivial at first for me because, well, these are gpaddles, right? These are basically MDLs that are being mapped in the Windows kernel. And this is not, this is not a buffer overflow. This is not a stack buffer overflow. This is not a heap buffer overflow. This is just a gpaddle overflow. And, what is that? Where are these things being allocated? Well, it turns out, something I didn't know because, again, not really an expert in anything. It turns out these gpaddles are actually allocated in a region called the system PTE region. And it also turns out that the system PTE region is where the kernel allocates all of the stacks. And so, well, if you're able to write data out of bounds of a gpaddle, you can actually overwrite the entirety of a kernel thread stack. And that's actually, well, that's kind of awesome, right? Because if you can overwrite a stack, you can overwrite a return address. If you can overwrite a return address, you can get ROP. And once you have ROP, you basically have code execution and everything's over. So the idea then is, okay, well, we can possibly place a thread stack behind our gpaddle. That's awesome. But how do I do that, right? How does that system PT allocator even work? And even if I understand how it works, can I actually control it? Can I actually interact with it from the guest? Because again, the guest OS is a guest OS. It can't just call fucking malloc in the host OS like that. It kind of has to do this in a kind of more covert way. So a few things. First off, how does the system PT allocator work? It's actually really simple. So that makes things easier. It's not meant to, it's not meant to be randomized or secure anything. It's not something that people are really meant to be interacting with, so that makes it easier. It's essentially just a bitmap, right? Any given bit inside that bitmap represents a single page. If that bit is set to 1, that means that page is currently being used. If it's set to 0, it means the page is not being used. So then the algorithm to allocate data is really simple. It's just, well, you just kind of walk that bitmap until you see a number of zeros that is big enough for you. You overwrite them all to be 1, and then, well, once you're there, well, you've allocated memory. Congratulations. The only thing that kind of complicates this is that you have a little cursor here, which is the little yellow thing in that bitmap on the right there. That's called the hint, and basically it's just going to be where the allocator starts walking the bitmap from. And so it's really that simple. Just to give you an illustration of how that works and how the hint is actually being updated after different allocations. Let's say that I want to allocate 5 pages. Okay, well, we have the hint in the middle there. Blue is 3 pages, so we can see that, okay, there's 5 pages there. That's cool. Let's just allocate those and then update the hint to be right after those 5 pages. Okay, that's the first example, really simple. Then if we want to allocate 5 pages again, well, what we can see is that we actually don't just have 5 pages right after the hint, right? So the hint has to start walking the bitmap until it actually finds what it wants. It's found 5 pages, allocates those, and it's all good. Now, the last example that is also kind of important is, let's say you want to allocate 17 pages, which is a lot of pages, and, well, you actually don't have that many free inside your bitmap here, right? It just kind of walks the entire bitmap, doesn't find anything. That's kind of sad. What it's going to do is it's actually going to expand the bitmap, just allocate a new block of 2 megabytes at the end of the bitmap, because it can kind of just do that, and then place its 17 pages in there, and then it just updates everything. The only thing that is notable from that last example is that when you expand the bitmap, you will always be placing your block in there, and you will never be updating the hint to be at the end of that block, which is not super important. It does come into play for the actual heap massaging that happens later, but it's not a super important detail. So after that, we need to actually be able to interact with that system PT allocator. Well, it turns out, because we have this ability to just keep sending receive buffers and send buffers over and over again, because that was the bug, right? Well, we can actually just we have an arbitrary size malloc into that region, right? We can just send a gpaddle that has an arbitrary size because the gpaddle is being allocated by the guest at the beginning. So it's the one that decides the size. And then it's always going to be mapped into that system PT region whenever we send it over. So we actually have a really good primitive to interact with that. The harder part is actually getting the host OS to create new stacks, right? Because it's kind of non-trivial. You're not supposed to really be able to tell the host OS, okay, can you just create new threads because I need some stacks, please? That's not something that's possible. Fortunately for me, there was at the time another bug in VM switch that just allowed me to basically get worker, so the system worker thread pool is basically just like a set of threads that can be used at a given time. And that's where the RNDisk worker threads are being created from, and other threads are being used. And so there was actually a bug that would get VMswitch to deadlock as many of those threads in that pool as necessary. And so they would never return. They would always show as busy. And so the idea is I can just like deadlock all the current threads, and then through normal operations, it will spawn new threads. And then I know that I basically get a primitive that lets me, spawn about maybe 5 threads at a time until I have to deadlock them again and create new threads if I need to. And so that's the primitive that I used. It's not ideal, but it is what it is, and it is what I had. So at that point, we basically just have a massaging strategy to place a receive buffer at a known offset from a stack. Normally, I would go through this, but I do want to spend some more time later on the actual mitigation, so I'm going to kind of just skip that. All you need to know is, I just basically do a bunch of allocations in a very specific order with very specific sizes to like kind of match the allocator. This is going to be placing my receive buffer there. Then I'm going to be placing another allocation, and then it's going to be spawning a stack right there. And so you end up with a stack at a known offset from the receive buffer. In practice, it's a little more complicated than that, and there's actually 2 different cases to take into account. But again, kind of just like gloss over that. Just trust me, this works usually. So the last thing here is, okay, so this is awesome. We can override a stack with arbitrary data of arbitrary size, basically, and that's great. If we can override a stack, we can override a return address to get ROP, and everything's awesome. Except it's not, because we have this little thing called KASLR, or just ASLR in general, which randomizes the addresses that code is at. So even though I can overwrite a return address and in theory get ROP, well, overwriting a return address is completely worthless unless I know what to override the return address with, right? I currently don't know where code lives, so I can't tell the CPU to jump to somewhere. I can tell it to jump to somewhere, I just don't know where to tell it to jump. And so that's what bypassing KSLR is all about. In practice, what I tried to do was bypass KSLR by finding an info leak bug, which turned out to not be too difficult, thanks to the way that the VMswitch message structure is made. What you can see here is you first have a header that is common to all these messages, but then you have a union of all the different message structures, right? That's what's being shown here. And what that ends up meaning is that different messages can actually have different sizes, but the struct that encapsulates all of these messages is always going to have the same size. And so what you might end up with is that, this is going to be at the top is going to be the memory that is actually used inside a message. At the bottom is going to be the size of the actual full message that might end up being sent back. And that was the info leak that happened. Was basically there was a struct for this whole NVSP message thing that was being allocated on the stack, as you do, but only these first 2 fields of the structs were being initialized, right? And even though only these 2 fields were being initialized, the whole of the structure, like the whole, 40 bytes were being sent back. And so that includes 32 bytes of uninitialized data. And that means I get 32 bytes of free stack data. And stacks, of course, very famously contain return addresses. And if I can read a return address, I can figure out where code lives at. If I can figure out where code lives at, I can just build out my ROP chain. And so that's basically that's just what this slide is showing. Is the final exploit is, okay, we use this info leak to locate VMswitch. We use that information to build a ROP chain. We overwrite a stack, and we get ROP. And then once we have code execution there, well, we can just kind of do whatever we want, which is great. We're done, except we're not. Because it turns out that info leak, as awesome as it was, only applied to Windows Server 2012 R2. At the time I was trying to target Windows 10, no info leak there, so oops. And that was annoying because I kept looking for a couple days, maybe even like a week for an info leak. I was getting very desperate, and I did not find one. So what I found instead was, started thinking, okay, I'm really desperate right now. Can I maybe bypass KSLR without info leak? And the answer to that is actually, surprisingly, yes. The thing to realize is, as mentioned earlier, actually control the size of the buffer and the offset of the buffer that's being written into the stack, right? And what that means is I can actually maybe do a partial overwrite of a return address. Because we know that each given module is aligned to a given boundary, On Windows, at that time, at least, I think it's still the same, but at that time, at least, it was 0x10,000 bytes. That means I can overwrite the lower 2 bytes of any given return address and know that it will still be within, within those boundaries. It will still be within that code module, and it'll still be like a valid code address, and I can even know where it's going to point to, right? So okay, that's kind of awesome. In this specific example, I'm overwriting a valid return address, which is supposed to be returning to this function, and pointing it towards the ROP gadget. And so basically, that gives me the ability to execute a single ROP gadget. And, well, is that useful? Yes. Taking a look back at our heap massaging from earlier, see, we had the receive buffer. We have a stack that is in an offset, the stack that we're going to be overwriting. Well, what I can do is I can actually allocate another shared buffer right after that stack. In this case, it's a send buffer because we're already using the receive buffer for something. And the fact that there's going to be a shared buffer here, you might be able to see where I'm going with this, is that if I am able to execute a ROP gadget that's going to increment RSP by a large enough value, RSP is going to end up being in my shared buffer. Right? And so that's exactly what I do here. I have this gadget here. I overwrite the lower 2 bytes of a return address on the valid stack, and then RSP is going to go up from all the way up there to all the way down here. And since that buffer is shared with the guest OS, as an attacker, I can just read and write values to and from it at all times. And that means that, okay, well, first off, what's going to happen is as soon as it tries to return, it's going to crash, right? Because it's going to try to return to address 0. That's not great. But what happens when a process crashes in the kernel is it's going to go through the exception handler, and the exception handler itself is going to start spilling data to the stack because it keeps using the stack. And at that point, as an attacker, I am able to read back a return address or whatever, figure out the ASLR values, like figure out where code is located at, and then I can also overwrite the return address and actually get ROP just by basically hijacking this exception handler in the kernel, which is super janky, but it does work. And so at that point, it's like, okay, this is exactly what I just described. You have a general protection fault. It starts spilling useful data to the stack, which is shared with the attacker. The attacker can start overwriting that data, get code execution, and it's all good. And at that point, we have gone through the exploit, at least in theory, like how it works, and we are hopefully going to see it work in action. I say hopefully because you never know. Okay, so is that it? Yes, that is it. Although I can't really. Oh, never mind. I can totally see. Okay, so where's my mouse? There we go. Okay, so this is a virtual machine. This is running on server 2012 R2 because I did not want you to see the janky version of the exploit. I want you to see the version that actually has an info leak, because hopefully it will actually work. So. I might kill myself. This just froze. This is exactly what happened at BlueHat, and I really hate myself. Okay, so I'm going to keep going through slides once again while I try to fix the demo, because apparently this computer does not like being on for this long. I'm really sorry about this. Oh, and this is not going to work. Okay, so what I wanted to talk to you about after the live demo, which is definitely still going to happen, is the work that we've done to actually harden Hyper-V as a result of this exploit, and not purely as a result of this exploit, in fact, just in general. This exploit has definitely motivated very specific mitigations that I'm going to go through, but we also do hardening work all the time, and that hardening work may have been helped by this exploit happening, but I don't want to take all the credit for that. Obviously, there's a lot of very talented people both doing the work and actually as well as thinking about what to do. So if I think about this exploit and how I would maybe break it, I think of 3 different parts, right? The first part would be vulnerability discovery, which is that if an attacker can't find a vulnerability, they can't exploit it, right? And it would be ideal for us to just find all the bugs, fix all the bugs, and live happily ever after. But in practice, that's not going to happen. That doesn't mean that we shouldn't be doing anything there either, though. And that's why, at least partially as a result of this exploit, we have done a great deal of reviewing work both into VMswitch and other Hyper-V processes, because doing this actual thing, like actually showing that this stuff can work, is a great way to kind of motivate people and show this is not science fiction, right? This is something that can totally happen in the wild, and we might not be able to see it. And so that would be the first part, is both kind of showing that this is possible and like doing this reviewing work, and then also we have the bug bounty, which I'm going to go into, and that's another big part of that. The second part is trying to break the actual exploitation stage of this. Right? If we break the exploit techniques that are actually being used as exploit, well, it's also not going to work, even if vulnerabilities still exist. So ideally, we want to just be able to break those exploit techniques, and that's part of the work that we're doing. And the last thing would be, well, even if the exploit happens, maybe it's not that big a deal. Maybe we can make it such that it's not that big a deal. For example, by making the targets less interesting, or like making technology that will actually detect the exploit and make it such that we can mitigate the attack as it's happening. All right, and so this is the first thing. I said this is the first thing. Hardening, this is actually the second thing. That was number 2 on my list. Hardening, one of the things that we've done as a direct result of this exploit was make it such that kernel stacks are no longer being allocated in the same system PT region as gpaddles. And as a result, this exploit would actually just be broken, right? Because at this point, we're overflowing outside of a buffer on the host OS, which as an attacker is still pretty awesome, but we can't override stacks. And we don't really know what's being allocated there. The only other things being allocated into this region now are MDLs. MDLs might still be exploitable while being overridden, but it is much harder, and you don't really have as fine-grained control over those, because typically those are going to be used by buffers, by drivers. They're going to be mapped in and out without you having much control over that, and so it just makes things much harder, maybe even impossible. So not just as a result, as a result of this exploit, this is something we did, and we know this would not just apply to this exploit, because out-of-bounds accesses from shared buffers have happened in other vulnerabilities as well. So this was the first piece of hardening. Another piece of hardening has been, is just like much more general, is going to be stuff like KCFG, which we kind of talked about in the previous talk, HVCI, just kind of there are more and more efforts to kind of enable that by default in more SKUs and such. In addition to that, you're going to have, more importantly, things like CET, which would, again, have broken this exploit. CET, which was mentioned in the previous talk, is the kind of hardware shadow stack stuff that would actually prevent you from overwriting a return address and just doing ROP. And, I actually just fixed the exploit, so let me just switch back real quick to my demo, which I swear the next time I do this talk, it's definitely going to work on the first try. Okay, so what happened here was I just tried this, right? I grabbed the channel, I did the exploit, I checked the status. The status here tells me that this actually worked, right? Nothing crashed or anything, everything is all good. So at this point, I can start doing stuff like listing processes in the host OS. Which, okay, that's not really super interesting, but because I actually have code execution, I can start doing stuff like injecting DLLs into random processes. So in this case, I'm going to try to pop calc by injecting a DLL in explorer.exe on the host. And you know what? Just think of how much more impressive that would have been if it had not failed the first time. Just like try to have that mental image in your mind. The next thing that I think is kind of cool about this exploit is like I wanted to show you that once you have control of the host OS, at least with the architecture in Windows Server 2012, there's definitely efforts being made towards things like confidential computing in Azure and such. Well, because I have control over the host OS, I can actually start messing with other virtual machines. And so an example of that is going to be, okay, so I can list various partitions on this computer. Okay, I can grab the guest. Number 3 is going to be the one to the right, hopefully. Start just doing stuff. And once that's done, I can actually just reuse that. I can list processes in that other VM, and hopefully... this is Windows 10, so it looks a little different, but... So that's the live demo, and just, God damn it again. I should really be more used to my demos failing, to be honest. And yeah, so the other few things I want to talk about are, well, we've talked about kind of breaking these exploit techniques, right? But the third thing that I was talking about is maybe we can make these targets just less interesting in general. And, well, that's actually possible. One way of doing that is, like I mentioned earlier in this talk, is we actually have VMSwitch was living inside the hostOS kernel. So once you compromise it, you just compromise the entire hostOS, and that's not great. But we do have a thing called vmworkerprocess.exe, which actually is a process that's spawned for each virtual machine on your computer. And, well, what if we start putting more components into there? What would happen is, if we're actually able to sandbox VMworker process better and just put more components in there, that means that compromising that component will only mean compromising that process, not the entire hostOS. So that's very desirable because that makes it a much less attractive target to attackers. Right? And so there are things that we are doing. The first thing is we're actually improving the sandbox on the VMworker process. It's still a work in progress, so don't go and take a look right now and chastise me. But it is something that's happening. It's better than it was a year ago, so that's something. In addition to that, we are improving RC mitigations on there. So that means that it's actually the most hardened process on Windows currently, in addition to like Edge. It's the only one with Edge that has CFG export suppression. We have forced CFG. We have only signed binaries in there, all that good stuff. So that's pretty great. And in addition to that, we are actually actively working on moving more and more components out of the kernel into that VMworker process. So we are hoping to kind of reduce that surface of interesting targets. However, because we are aware that our code is not perfect, it will never be perfect, we have been making efforts to kind of try and open up and partner in a way with the InfoSec community, right? And the main thing to do with that I want to talk about here is the bug bounty. For this exploit that I just showed you, that took me a little over a month to develop, we would pay you $250,000, which is not a bad salary, I would think. And I think that all of you that are interested should start looking into that. And because I want to help you do that, we have started doing things like publishing public symbols for a bunch of these binaries, as well as publishing source code for the Hyper-V Linux integration services. So that means that you actually have full source code for clients to these VSPs. And so that should be a great way for you to start experimenting with stuff. In addition to that, at BlueHat this year, we had a talk by our own Joe Bialik and Nicolas Joly about how to start getting into Hyper-V vulnerability research. And so just check out that talk. It's pretty great. It will give you a lot of pointers as to how to get started. And, well, thank you for your time. If you have questions, we're out of time, so just, come over. Thank you.
We have time for questions before we go. Any questions? I think everyone's fleeing for the party.
Cool.
Thanks, Jordan. That was great.
Thanks.
Good talk, man. Good demo.